Yes, please. Yes, please.
Okay, thank you. Everyone, welcome back to the rest of this lecture. So in this lecture, I'm going to introduce this work about Top Insight. It integrating topic modeling and large language models for question generation task. So here, instead of topic modeling, using topic modeling directly to address some real-world application, so this work use large language models to assist the interpretation of the topic modeling results. This work is presented in Australian Data Science and Machine Learning Conference in 2024, and is currently in price and will be available online very soon. So for this work, I'm going to focus on the motivation and also the challenges. Specifically, why do we need large language models for this kind of topic modeling task, and what are the benefits of combining large language models and topic modeling techniques to get together. And finally, I'm going to introduce these top insight frameworks. Here are some background knowledge. So in real world, there are various data collected from users regarding the products or service from a company. Here are several examples of those kind of data. So for some telecommunication company, there exists lots of conversational data between customers and agents, so not just telecommunication. I think most of the companies, they have this kind of conversation data stored in their database. So those are interactions between customers and agents regarding their problem toward a very specific, like their customer's problem. And as for these, like for example, for some hotels, there exists some review data. So customers will share their experience during their stay at a certain hotel, or sometimes the reviews could be for some certain theme parks, for example. And one example are some Google reviews, which are available online. And finally, within some organization, so some departments, they tend to send out those surveys with open-ended questions. So the answer to the surveys are some text, for example, their satisfaction regarding the company, or how they are disappointed toward the company's management skills. So those are kind of customer service data. And now the question is, given those millions of data collected within an organization, how could we obtain some insightful questions from this vast amount of user feedback data? So, for example, within a company, they understand that there are some general questions regarding their service, but it's really hard for example, the management team to locate the specific pinpoints from it. And here are some examples of those kind of general questions could be identified from this kind of data. For the first example, there exists conversational data between customers and agents. Some common questions may ask about their problems regarding the service or the products. For example, suppose it is for example, the telecommunication company. The customers tend to ask questions about how to start an account and also why they cannot log into their account. So things like that are common. And as for these review data sets, for the low rate reviews, so the company would like to learn what are the most common complaints so they could potentially improve given those kind of questions. And finally, given these surveys, within an organization, they would like to understand some general pinpoints within the organization of the company so that they could improve the potential, for example, management within the company. So that's the motivation of why we need to understand the general questions within an organization. So however, to complete this kind of task is not that easy. The first challenge is regarding the large-scale data analysis. Usually, those kind of data are quite large in terms of the volume. Sometimes because it's too large for manual analysis, so the company expected to have some automation method to analyze the general questions. And another challenge is that the data itself are unstructured. So for example, it cannot be analyzed through some simple Excel, for example, graph generation method, or for example, they cannot just summarize the data, for example, the most frequent word. For example, it could be some stop words or the name of the company or the device name. And those are not actually meaningful in terms of this kind of task. So unstructured data can result in various in content regarding the documents or the reviews they got. And this could make it difficult to identify consistent patterns or themes because our goal is to understand some general like pinpoints. And another challenge is how to automatically generate some insight and or the questions given this large volume of data. So the first thing is that those kind of generated things should be human readable. It should use some consistent language and understood by human being. Otherwise, it could be just some word without any context information. So even though we got some pattern, it's really hard for the management team to analyze it and obtain some conclusions. So in general, what we want are some actionable like things or the sentences. And another challenge is the vague or overly generic statements. So for example, we may depend on some generative methods to generate the statements. However, because of the volume is there, the summarization could be overly simple, over simple, and that not make sense. Let's back to that telecommunication company example. So for example, the answer from the machine could be that customers have some complaints regarding our service or regarding our network service. So those are something like the common sense learned by those management team. So and this kind of question generated are actually not good summarization in terms of the pinpoints. And let's go back to existing methods that could be helpful on addressing these kind of challenges. The first method could be topic modeling. So we've already covered a lot about these topic modeling techniques. So techniques like LDA per topic or maybe the VAE could be used in real world scenario. And for topic modeling, as we covered before, each document is represented as a set of topics and a distribution of associated words characters each topic. For example, a topic could be a topic could include words like room, theme, data, and plan. And then if you have some domain knowledge regarding this kind of term, you will understand the customer's question would be some international roaming service. But the problem is those lists of words are not always human readable. So we don't know the exact story behind those kind of words. And this happened, and this problem severe within a certain domain. For example, our data are all about the telecommunication term, or sometimes our terms are all about, for example, a biomedical term, then the generated topics could be hardly to be, so the story behind the topics could be hard to be tell. So that's the limitation of these topic modeling methods. And another option is large language models. So, so basically some Gen AI-based large language models, for example, the GPT-4 or the Llama 3, and also things like Falcon. So the benefit of large language models is that they can generate human-readable, interpretable summaries from large user feedback documents and leveraging the natural language-based instructions. So the idea is that we are going to give some prompt to these kind of large language models. For example, it could be, could you please summarize the following documents into some general pinpoints? So that could be one option. But the problem is some method has token limitation and cannot feed. So in that case, we could not feed all the documents altogether. So recently, I think for the latest Llama 3.2 model, we can input up to, I think, more than 2,000 tokens, which are quite a lot. However, it's still not enough given like millions of documents. So because of the technique limitation and the requirement to fulfill this real-world question, we propose this top insight framework which combines the topic modeling technique and the large language models to generate some questions. So here is the framework of the top insight. So we given multiple documents. The first step is to use this topic modeling technique to obtain some topic words. So as we introduced in the morning session, we will conduct this topic document embedding for each document. We conducted different kinds of topic modeling methods. Options are, for example, VAE topic modeling, and some methods could be the LDA or BERT topic. And using this model, it can generate some topic words, which could be represented like this alpha K. K represent one topic, and we have totally uppercase K number of topics. And given this alpha K, for each topic, we are going to conduct the topic guided document retrieval and also the question generation. So those steps for each topic generated. And the first step we are going to do is to obtain the most relevant documents for each topic. So what we are going to do is using this cosine similarity. So we embed each topic using some embedding method, like, for example, BERT. And then we calculate the cosine similarity between this one and the document embedding. Once we obtain the cosine similarity, we only choose the top M retrieved documents from this dataset. And now those documents XK represent the topic relevant documents. Given these kind of documents, so here the number of M is much smaller than the original documents. For example, we only choose the top 100 documents from here for each topic, and then we generate the questions through using a prompt and also large language model. So the large language model will generate the common questions given these XK documents. The problem of this insightful question generation is formulated as follows. Let X with X1 till Xn number of documents be a corpus with n documents where each document represents a sequence of user feedback data in a single chat session, or it could be from one review. The objective of this IQG framework is to identify K most insightful questions, Q, representative of issues and concerns raised in the conversation data. The first step is topic discovery. So I think most of you are familiar with this topic modeling methods right now, but here are some mathematical representation of this method. So for a corpus X, it is assigned to consist of topics denoted as Z equals Z1, Z2 till ZK. So those are the latent topics, where each topic corresponds to a group of similar user queries, with this K equal to this K from the representation from the latent topic from the generated questions. So the idea is we assume that each topic generated from the topic modeling methods correspond with one question generated by this large language model. So this is our assumption. And and when you apply this kind of method, you may adjust it according to the results and because of the quality of the data set. And a document X contains multiple topics. So a document is again represented as this, this is the word. A document is again represented by a distribution of the word containing V words, and this can be represented as a mixture of topic through this formula over here. And if you remember, this also appears in the previous multimodal topic link methods. The only difference is that now we only have one input, which is text. So basically, one document X is represented as a mixture of multiple documents. And the goal is to predict those kind of words because so for the statistical generative method like LDA and BERT topic, not BERT topic, and VAE. So here the ZK represents a topic and corpus X contains K topics. Okay, so so that's the step 1, which is the topic modeling method, as we mentioned in previous session. Step 2 is about topic-guided document retrieval. And top insight uses the top B words of Ti given ZK. So here is the generated like the word distribution, and we use the top words representing each topic ZK as the query alpha K. So in other words, it can be represented as this way to retrieve the most relevant documents for case topic using cosine similarity as follows. So here we represent the retrieved document in this format. Essentially, what we need is the top M documents that are most similar to the topic embedding over here. For the last step is the question generations through large language models. So large language models can automatically generate text given a natural language-based prompt templates. Mathematically, the generation of each question QK, where L is the length of the generated question QK. So here the omega 1 till omega L represented the output length of this large language model. So I think we will cover this kind of thing in tomorrow's session and also next week. So for most of the large language model, you can have a max token, that max generated token. You can set something like that to restrain the generated word length. And the word could be generated through this chain rule. So to generate the first token, it depends on the given documents. It also depends on this kind of prompt we assigned. So it can get the large language models, which represented by this, to generate the first token. And then to generate the next token, for example, token 2, it depends on all the previous, like the input. So for the decoder only model, which is a structure of most of the large language models, such as Llama and also the GPTs. And here I'm going to introduce some experimental details, because the goal of this work is to propose a framework that could be usable in the real world scenario to understand some general questions. So the experimental result here, we evaluate the output of each step. So for step 1, we tested different kind of topic modeling methods. It includes the clustering-based methods. So per topic, we've already covered in previous session. And another one is contextualized non-negative matrix factorization and also k-means. So non-negative matrix factorization is similar, is aimed for dimension reduction. And given the reduced dimension, we use these k-means for clustering. So we will not cover the NMF here in this tutorial, but essentially it's a very good method, and I think if you are familiar with it, so you can try this kind of method in your work for topic modeling. And another category of methods are those statistical methods, which include the zero-shot CTM and also the CTM. So CTM, called the contextualized neural topic model, it also uses the variational autoencoder as the backbone framework. And for the input, it includes the bag of word and also the BERT embedding, for example, the sentence BERT output or other kinds of the input. So that's the CTM, and the zero CTM is very interesting. So they are proposed by the same group of the author. So for this zero CTM, they just took the BERT embedding as input and forward it to the encoder part. And for the output, they recover the bag of word embedding. So I think you can imagine for the inference part, it's solely relying on this kind of context information. And for the decoder part, it aims to generate these bag of words, which is document representation. So the reason these two are statistical methods, as we mentioned before, because they are based on some statistical framework. And essentially, each document is represented as a mixture of topics. On the other hand, over here, for these clustering-based methods, each document is assigned to one topic. So we are going to test it. We are going to test the framework on 3 data sets. So those 3 data sets are obtained from Kaggle. So those are some review data set towards the Disney, Sephora, or the Universal Studio. And for all the documents, they have different kind of lengths, different kind of document length, and also number of documents within each data set. So note that for those kind of documents, because they are review data, so they come with a rating regarding the review, and we only filter out the low rate review data given the original data set. And they are from different domains. For example, Disney and the Universal Studio are regarding their theme park, and the software are about the skincare product review on, I think, millions of the products they provided. So here are the topic modeling results. So in this figure, I'm using elbow method to evaluate, to choose the hyperparameters for this CNN, which is the NMF-based method, and also zero-shot CTM and also CTM. So the point here is that we don't know what is the optimal number of topics for those kind of model given the data sets. So what we are going to do is we empirically tested the topic quality for different number of topics. So here, according to the data sets, I tried, for example, 5 to 50 for Disneyland and Universal Studio. For Sephora, because it is relatively larger, I tried up to 200 of documents. And as you can see over here, so the optimal point, what we want to find is this elbow, is this like the changing point. So after that, the topic quality will be dropped. So that's the point we would like to find. And let's take another example is, so for example, this blue one, which is a NMF method on this Disneyland dataset. So again, 10 is the optimal number of topics for this method on this dataset. So as you can see, trying this number of topics is quite empirical, and people tend to use this method, or alternatively, you can use the ciliate number to evaluate the number of the optimal number of topics. And here are the summary of number of topics we choose by using this kind of method. And for per topic, because it's use density-based clustering method, and HDB scan, which can automatically decide what are the number of topics for given a data set. And as a result, per topic generated a large number of topics for all the datasets. And here the CV represents the coherence value. IRBO represents the inverse rank bias overlap, which represents the diversity. And we use the quality to choose the optimal number of topics for each method, because sometimes, as you can see, the method could get a very high coherence, but the diversity is relatively low. So using this one is more straightforward. And another thing is that we noticed that given these three data sets, per topic also generated a significant number of outliers. So for the Disneyland datasets with almost 8,000 of documents, it generates 4,000 outliers. And for the Sephora dataset, it's over 16,000. And also for this Universal Studio, it almost generates half of the outliers. So that's one of the drawbacks we observed from these kind of experiments. And the right and the value highlighted in red over here represent the highest topic quality over these four methods on each data set. For example, for this Disneyland dataset, the NMF method generates the best topic quality. So we are going to use this NMF method, topics generated by this NMF method to generate the questions. And for this Sephora, we use 0CTM and CTM for this one. So here we manually check the topics generated by different kind of method. Here are some examples generated by this Sephora dataset. So as we can see, for topic 1, so we select the top 10 words to represent each topic. For topic 1, it contains words like weather, perform, wheat, tarty, reasons, truth, aspect, boom, thus watermelon. It looks like it's some feedbacks regarding some products with this kind of watermelon things, flavors. And the second topic contains sensitive, first-time use, face-used acne skin product using. So it looks like discussing using certain product for sensitive skin or the acne skin. And in general, those topics generated by 0CTM, they represent different kind of topics, which is good. And within each topic, it looks like we can understand, we can generate a story, but it's not that like straightforward. For example, here topic 6, it means it may indicate some like negative effect of some product, which can result in the red of the skin and the pimples and so on. So that's why we need large language models to generate a story, like tell us what exactly happened given each topic. Another purpose of show you this kind of topics is to validate the quality of the generated topics, which is also referred as like the manual evaluation mentioned previously in our slide. Okay, so now we have obtained the topic words for each method. Here, step 2, our goal is to retrieve the optimal, the top M number of documents given each topic. So here we only choose the top 10 documents. Top 10 documents for each topic. And someone mentioned why using cosine similarity. So this idea is from that zero-shot, like the zero-shot learning. So usually in zero-shot learning, you can people use, so in literature, people use cosine similarity to obtain the documents. So it's one of the default method to do and show some promising performance on previous NLP methods. And you can also try different kind of similarity methods to obtain these top documents. So here we reported the average cosine similarity scores for all documents and also compared with the top 10. So here for the all documents, the average cosine similarity is relatively lower than the top 10, which so the only purpose over here is to show that the top 10 documents are more similar to the regarding a topic compared with feeding all the documents to regarding a certain topic. And here we also plot the cosine similarity distribution for one topic, which is queuing day hour. It is from, I think, the Disney dataset. So the topic is about the queuing time. And given all the documents within the Disneyland dataset, only few of them have a relatively higher cosine similarity comparing with all the rest of them. So that's the purpose of this density function. So on the contrary, for some certain task, for example, in a certain domain, for example, the bioinformatics, because the document embedding could be low quality. As a result, the density function will, for example, only focus on, for example, there's 0.1, indicating that actually all the documents do not have a very good similarity with these topic words. And in that case, this topic may be not good or the document embedding fails. So we may need to refer back to these kind of steps to check what's going wrong with this framework. And finally, we are going to generate the questions with the large language models. And to evaluate this kind of generation quality, or we use the automatic criteria, including the perplexity, grammar errors, and distinct 3 scores. So for perplexity, we use GPT-2 method to evaluate the probability of generate the next word given a sequence of tokens. So if you are familiar with the pre-training language model, you may familiar with this kind of perplexity concept. Basically, it aims to evaluate the coherence of the generated text. So note that we also mentioned about this coherence and diversity concepts in evaluating the topic modeling. But here, the idea of the evaluation is in terms of the generated text given a paragraph generated by the large language model. We want to understand if the generated text are coherent and also distinct instead of just simply repeat certain words multiple times, which is a kind of hallucination. And for this grammar error, we use some spell checking tools, which is a Python library available online and open sourced to do the spell check according to some dictionaries and grammar checking against some language rules. So those are not some machine learning method. Those are some NLP methods that define some certain rules regarding this kind of language and detect the grammar error. And this distinct 3 is like the trigram of the sentence, and it counts the ratio between unique trigrams in the summarized text and the total number of trigrams in the text. Aside from this automatic criteria, so usually in application, it also relies heavily on this human evaluation. So human evaluation usually we need to find certain experts. For example, in our case, we have 3 experts to manually evaluate the relevance. For example, relevance here is about how well the generated questions capture the insights from the selected documents. In other words, if the generated text align with the documents we provided in to the large language model. And it also evaluates the consistency of whether the content and the sentiment of the generated question match the original documents. For example, sometimes the documents refer to for example, the bad smell of a certain product. However, the generated documents could be, for example, this product is good, which is also a kind of the hallucination. So those kind of sentiment in alignment is something we need to focus in the human evaluation process. And finally, the coherence and the fluency criteria evaluate the lexicon and the grammar aspects of the generated questions, determining their human readability and linguistic accuracy. So fluency means it's straightforward, like if the generated sentence are fluent or it jumped everywhere, like it mentioned the product, then it mentioned something else. And the coherence also is about the language itself, like the lexicon thing, and also the grammar things between words and also between sentences. So here are the results of these generated questions. So for these results for automatic evaluation, so sorry, here I forgot to mention, we tried different kind of large language models to generate the questions given the topic, the topic retrieved, like the documents and also the prompt. So we tried this GPT-2, which is relatively small model compared with others. And we also test the Falcon 7B, which means 7 billion of the parameters, and the Llama 3 8B. So while we are conducting these experiments, I think the Llama 3.2 is not available. So that's why we test this 8B, and also the GPT 3.5 and also the GPT-4. So in terms of the perplexity, it looks like the GPT-2 performs best. One reason is that when we do the evaluation, and similarly for most of the previous works in the literature, we usually use this GPT-2 model to evaluate the perplexity because it comes with the analyzation of this perplexity. If you are interested, feel free to check online how does it do that. So that's one explanation. And as you will see if we analyze it by human, the generated results are actually not that good, not that coherent. And in terms of grammar error, looks like GPT 3.5 and 4 are performing very well without any grammar error. On the contrary, for this Falcon and the GPT-2, they tend to make some grammar errors. So here 4 means on average for each generated text, they have 4 grammar errors. And finally, in terms of the diversity of the generated text, so here the higher the better. So for GPT-4, it generated slightly better generated more diverse like text compared with GPT 3.5 and others. So that's the result of the automatic evaluation. What we learned here is that GPT 3.5 and 4 looks very promising, and it seems that this perplexity is a little bit biased. And for this table 7 on the right-hand side, those are results for human evaluation, where we have 3 experts to manually check the generated text given for each topic, and then calculate their average performance over the topics and also over all these kind of data sets. This result is also average all the data sets. So here we have on the scale of 5. So the higher value represent better performance. So as we can see over here, so the human evaluation results indicate GPT 3.5 and 4 tend to have significantly better results compared with other models. It tend to generate more relevant and consistent results compared with other methods. So here are some examples of generated questions. So to generate those questions, we are using this prompt. So the prompt is like, what is the most common question that customers complain about in the following reviews? And we restrict the number of questions in the prompt. And also like when we do the coding thing with the large language models. So we will cover, I think, in the tutorial tomorrow. So for example, so here we give a large language model an example, because we found that if we don't use this kind of format, so it tends to generate a summarization instead of a question, which is the expected format as we want. And after that, we given the original documents, so 10 documents in these kind of experiments, and we forward those kind of things to large language model and generate the questions like these for each method. So I think, again, maybe Stefan or Joy will mention in the lecture. So basically, this kind of method is a way to do the prompt engineering thing, like we include all the relevant documents using the topic modeling methods. So let's quickly have a look at the results generated by each documents. So for this GPT-2, we found it suffers from the hallucination problem, because here the context is that we gave the several dataset for the first topic we just saw about that watermelon thing. And the GPT-2 method seems generate some random things which are not even relevant to the original context. And for these Falcon methods, the results is more human readable, but again, it failed to identify the most relevant context or according to our instructions. So for this Llama 3B, actually the results are not bad. For example, the first thing over here is that the product has strong and please smell, which is mentioned heavily in the documents we provided. So this is good. However, the format is not something we can use directly. So for example, use it as some actionable rules or address it directly. So that's the limitation of this Llama 8B. So if you can try a higher version, for example 3.2, the performance could be improved compared with this Llama 3. And finally, for this GPT 3.5 and GPT-4, it generates the things generate text in the format that we want, and also it makes sense given those documents. So this framework has been applied in some real-world platform. So here we use this method in a telecommunication company here in Australia while I'm conducting the internship. So the background is that customer service is vital for those kind of companies. And their goal is actually to implement the chatbots powered by large language models, allows these companies to deliver prompt and scalable response to user inquiries and complaints. So their goal is to build a chatbot. But prior to that, they need to understand what kind of questions are mentioned commonly by their users, so they can build the chatbot accordingly based on large language model and also other kinds of rule-based methods. So for this work, so the framework is deployed in the cloud service, and it accesses the datasets from the company to do the topic modeling and also other parts. And finally, the generated results are used to build this chatbot. So in this work, different from the experiments we showed before, we have much larger documents, about 150,000. And on average, the documents are longer than our previous, the datasets, baseline datasets used in the experiments. And for the document embedding, because of the limitation of this cloud environment, we can only access to certain kind of embeddings. And here we are going to use this text embedding ADA 2 model, which is provided by the OpenAI or OpenAI. And for the dimension of the embedding space is 1500, which is larger than the big BERT-based method we used in previous method. And for the topic discovery method, we use this NMS method given this document size and also the flexibility of this NMS-based framework. So for the generated question, so we set the number of topics to 300. And after we obtain these generated topics and also obtain these documents, for step 3, we use this ChatGPT-4 or GPT-4 to generate these questions through the OpenAI API. Here are some obtained like topics and also the questions generated by our framework. So we found that the performance is not bad, and given a better like the embedding method compared with the BERT-based, actually the identified context has some finer granularity. For example, so here we obtain license, iPad, passport, prepaid SIM. So if we directly look at this kind of word within the same topic, it's really hard to tell what kind of information it want to tell us. However, with this kind of generation framework, we can understand that the customer may want to use a SIM card for mobile internet on multiple devices, including smart TVs and also this kind of iPads, without a passport, for example, to log in, things like that. And another example would be this Samsung Protect iPhone upgrade. So without, for example, working in this customer service domain for a long time, it's hard for us to detect what kind of contact information. However, this framework can detect that can I keep my current device while upgrading before the end of my contract. So that's how we use it in a real life scenario. So to summarize, for this work, we propose this top insight framework for question generation, and we conducted experiments on 3 open source customer review dataset and also a case study. One limitation of this current platform is that it heavily relies on the human evaluation to validate the quality of the generated questions due to the lack of ground truth data for the generated results. Because basically what we want to learn are some unknown information given the big data. And in the future, we are going to design some LLM-based evaluation method, and think actually Stefan will show you how to evaluate how to use LLM-based evaluation method tomorrow to assess the quality of the generated questions automatically. And another thing or feedback we got from the audience is that it will be more useful to generate some mechanism to adjust the granularity of the obtained topics. For example, for certain scenario, we want to know the details, like the very specific points of the pinpoint, like the telecommunication company example we showed before, because our goal is to build a chatbot. So the more comprehensive, the better. However, for some scenario, we only want to learn some more general things so we can action quickly. So things like that will be useful for this kind of framework. And that is section 3 about the top insight framework. That's how we integrate the topic modeling with the large language models. And before we dive into the tutorial section, I'm going to summarize this course. So basically, this course explores how Gen AI enhances topic modeling, focus on foundation techniques like VAE and their applications in multimodal data and insightful question generation. For Gen AI in topic modeling, it offers better semantic representation than traditional methods, and it offers flexibility to incorporate this kind of multimodal data, even though we only show the use case in the image text domain. It could be further used in, for example, video domain to generate the topics for some videos. And the role of VAE is to map data to a latent space and capturing rich topic distributions compared with a autoencoder, which only map to a deterministic latent space. We also introduced these multimodal topic modeling methods that combines text and images to enhance the topic quality and provides actionable insights. And finally, for top insight framework, it can automatically summarize its application in generating insightful questions from large datasets using a combination of topic modeling and large language models. So the Gen AI for topic modeling could potentially have a broader impact in the real world scenario. So in real world applications, it could be applied to customer feedback analysis for business insights, It can be used to build the chatbot, to generate some user questions. And the multimodal data integration could be also useful for the e-commerce, healthcare, and also social media analysis with these kind of multimodal topic modeling methods. There is a potential of transformative. So Gen AI is enabling more accurate, diverse, and interpretable topic modeling systems. So that's how Gen AI combine the impact of Gen AI with topic modelings. So here we briefly introduce some possible future directions based on our previous lecture. So there is a need to generate better semantic representations with the integration of Gen AI model. So for example, one feedback we obtain from that multimodal topic modeling methods is that we could potentially use that CLIP method, which is one of the multimodal Gen AI methods that can align the image and text all together. So those kind of semantic information provided by the Gen AI large models could potentially benefit the quality of the topic modeling methods, for example, generate a finer granularity of the context information. And another direction is dynamic and evolving topic modeling. So this part is mentioned in the example, so the journal paper of Log4j, so by Joy. And there is a need to learn the temporal topic modeling, for example, over certain times, what's going on, and for the rest of time, what will happen for the rest of the time. Like if we could generate some real-time topic modeling for continuous updating data streams, this could be a challenge for some of the large language model due to the efficiency of generate the text given the large size and also the size of the documents. However, it can potentially, for example, identify more accurate about lifetime topics shared within one community. Other directions are about, for example, integrating text with other modalities. So Gen AI can enable topic modeling across multimodal data. And it is possible, for example, to combine those media posts with text and image. For example, right now, GPT-4 becomes multimodal, and also for the Llama 3.2. So it is possible to automatically generate some multimodal analysis. However, it may have certain challenges on doing those kind of tasks. And another thing is about cross-modal generation. For example, we can only access to the video data. Could we generate some topics shared by this kind of topic modeling, this kind of video data? So we no longer get access to the text. We only have the multimedia input. Could we generate some text things? And finally is the enhanced topic coherence and the interpretability. Those are things like we mentioned in the top insight framework. So generative topic models combine these topic modeling and generative AI can produce more coherent and interpretable topics by leveraging the generative power of deep learning. And again, and another thing is how could it is possible that we can control the topic generation with those kind of Gen AI method. For example, could you focus only on the healthcare related topics? So the real world data is always noisy. And maybe sometimes we only focus on a certain domain, but topic modeling methods is not that within our control. It can generate something irrelevant. With this kind of Gen AI method, could we leverage this kind of technique to generate more specific topics across the big data? So now we have finished. Now I have covered all the sections about the lecture. So we can have a 10 minutes break prior to this tutorial, and I'm going to share the data with you for this tutorial. So you can have a break now.
So dear participants, it's a 10 minutes break. We'll come back after 10 minutes. In case of need, kindly write on chat.
Hi everyone, welcome back to this tutorial. So I just shared in the chat about the link of the dataset. So on the platform, I think on Turnitin, we cannot directly share this dataset because it's too large. So we share it through this Google Drive. It's approximately, I think, 5 gigabytes. Could you please download the dataset in that link and let me know if it is working? If not, I'm going to share it again. Okay. So this tutorial is about the multimodal topic modeling paper we discussed in the second session. It's called the Enhanced Topic Modeling with Multimodal Representation Learning. And before that, please let me introduce this book written by Professor Richie Nayak and also Dr. Kang Leung, who was a postdoc and a PhD student advised by Professor Richie Nayak. So this work is about multi-aspect learning. So multi-aspect is a more general terms than multimodality. In multimodality, we only care about data from different kinds of modalities, for example, either image or text. But multi-aspect learning is basically everything. For example, it includes not only the multimodal, but also things like the multi-view data. For example, multi-view means the same sentence we collected from different kind of the same scenario we collected from different kind of language, or sometimes the same incidents we collected through different kind of newspapers and social media. So things like that. And this book offers a detailed and comprehensive analysis of multi-aspect learning, focusing especially on representation learning approaches for unsupervised machine learning. For example, the clustering algorithm. It covers state-of-the-art representation learning techniques for clustering and their applications in various domains. For example, in multimedia, or not only just in NLP, multimedia, and others. And this is the first book to systematically review the multi-aspect data learning, incorporating a range of concepts and applications. And additionally, it is the first to comprehensively investigate manifold learning for dimensionality reduction in multi-view data learning. So if you are interested in this kind of unsupervised learning and also the manifold learning, specifically for dimension reduction, please check this book. And it also covers the latest advances in matrix factorization, which we didn't have time to cover in this kind of in this lecture. Subspace clustering and spectral clustering and deep learning methods. And so this is the publication information of this work, this book. And before we started the tutorial, please let me acknowledge this work about contextualized topic models. So this is the one we used as referred as CTM and zero CTM in the top insight framework. Most of so our multimodal topic modeling is built on this project of contextualized topic models. And I put the link of the paper and also the GitHub project of these contextualized topic models in over here underneath the bottom of the slide. So if you found this CTM method useful, please set their work and also refer back to this project. So first, I'm going to introduce the data set we are going to use. It's called the MMMDB, which is a multimodal data set. So this data set is a benchmark for multimodal learning, particularly for movie genre classification. So that's the task. And it is a multi-label classification task originally, including the 25,000 movies. So it's not that so it's not a small data set. And each labeled with one or more of 27 genres, making it challenging for multi-label classification task. The dataset provides textual metadata such as plot summaries, and it also has the image modality, which is a poster. So if you find this dataset is useful, you can find the link available over here. So in this link. And the citation of this dataset is in these gated multimodal units for information fusion, which is published in SELR Workshop 2017. So here is how the MMMDB dataset look like. So given the time string, I don't have time to show you this kind of like input data, but here are two examples. It has this poster aligned with the description or summarization regarding this, like this movie. And for the original data set, they also have the label information for each this kind of multimodal data. However, we are going to use this data set for topic modeling task, which with an unsupervised manner. So we don't use the label information within this like data set. And here is a quick recap of the GDF NTM framework. So we have this forward path with this gating mechanism. The input are those three modalities and gating mechanism, and also the neural topic modeling module for generating the topics. So first, I'm going to describe how we obtain the image and text embedding. So if you download the dataset through the link I provided in the chat, you will find that there are embeddings instead of raw data. So for these embeddings, we use VGG19 for image representation and Roberta for text representation. So because obtaining the embedding for 25,000 of documents is time consuming, so to efficiently like conduct this tutorial, we directly provide you these two embeddings for the documents. But keep in mind, you can not directly use it in the research work. You have to get your own like embeddings in your work. So, but we will introduce how we obtain this kind of embeddings. So for this VGG19, it is a deep convolutional neural network with 19 layers. It composed of sequential blocks with convolutional layers, max pooling layers, and fully connected layers at the end. So its uniform structure introduced by the visual geometry group emphasized simplicity and depth, making it effective for image classification and feature extraction. So that's some introduction about VGG19. What we need to know is that this VGG19 is a CNN-based framework. And also it has 19 like those kind of CNN blocks. What we are going to use is this final block after these max pooling layers. So the dimension will be 7 times 7 times 5 512. So we are going to use the output of this layer as the image embedding, and we will transform this kind of format a little bit later in the network structure. So keep in mind that VGG19 is proposed in 2015. It's still a very, very popular method in multiple domains of computer vision and also multimodal learning. However, some people may argue this VGG19 is not the state-of-the-art method. So you can use, for example, vision transformers, or if you are keen with CNN, use the ResNet as your backbone network for image extraction. So for the text domain, we are going to use Roberta embedding to generate these sentence embeddings. So as we introduced in the first section, so given a sentence, we generate the token embedding for the sentence, and then we use the average pooling to obtain a document embedding for each sentence. And similar as that VGG, so for the Roberta embedding, we already provided in the dataset link in that zip file. And what you obtained are the output of the final layer of Roberta base model. So for Roberta base, it has 8 like transformer blocks. And we took the output of the final transformer block and calculate the average. And it comes out the embeddings, the one we currently share. So that's the contextual embedding with image and text. So for the data preprocessing with bag of words, we are going to conduct multiple steps like remove emojis, stop words, etc. And I think now I would like to share the screen of the code, like for the Jupyter Notebook. So again, don't forget to download this MMIMDB dataset. And so that's our project about called this codes tutorial 5. If you download it from Turnitin and unzip it, and you need to like put this dataset under this data and MMIMDB like folder. So under this folder will be image, NPY, raw text, and also this text Roberta files. So it is like structured as this. It is underneath the data MMIMDB folder, so something like this. So I'm running it on Jupyter Notebook, but feel free to run it on your own platform like Google Colab. I think Colab will work well because we tried it, and or on your HPC environment. So the notebook we are going to use is this one, GDM NTM. It's relatively simple and not complex. It only contains this kind of I think 12 blocks. So all the other informations, including the pre-processing codes, network structure, and also models, they are included underneath these files. And I will introduce the critical like functions, classes underneath these files. But right now you can just focus on this like this GDM NTM notebook. So the first step is to load the different kind of libraries. I think for some of you, you may need to download these NLTK packages and scikit-learn and also these GenSim packages. For NLTK, you may also need to download these stop words, which will be used later in the data preprocessing step of bag of words. So this first block is all about including different kind of libraries and also packages from our utils, module, and network folders. So the first thing we are going to do for this GDM NTM model is to generate the pre-processing and generate the bag of words. So the first thing we are going to do is to load this raw text. So raw texts are text with the raw data without converting to numerical formats underneath this file. And we are going to do some cleaning function for these raw texts by using the clean text and remove emoji function. So those two methods are available over, let me check, are underneath this util function in these pre-processing steps. So it's over here. So as you can see, basically it uses regex to replace, for example, URLs and mention users or the emojis. Because while we conducted this project, certain documents are collected from social media. So that's why we need lots of pre-processing steps over here to obtain the bag of words. And since bag of words is purely depends on the word frequency, those kind of noisy information may affect its effectiveness. That's why data cleaning is essential to obtain the bag of words embedding. So you can check the code later for these two steps. After that, we got some clean text, and we forward this one to this class white space pre-processing stop words. So again, it's underneath these pre-processing steps. So this one, essentially, what it's going to do, it is going to further do some pre-processing steps. For example, remove the punctuations, convert everything to lowercase just in case there are two different vocabulary represent exactly same word. It will also, for example, remove this kind of extra white space, and it also uses count vector to convert it into this bag of word representations. And it processes each document iteratively. So it may take some time to do this step. And the output, as you can see over here, are 4 things. The first one are the pre-processed documents. And then it also gives you the unpreprocessed documents. the vocabulary of the bag of word and return the indices. So I think one thing I didn't mention is this vocabulary size, which is a value we need to predefine for the for this class. So here we set a cap to 5,000. So that means we only choose the 5,000, the top 5,000 most frequent words if the document, if the corpus is too large. And that is because when we do the reconstruction loss of these VAE-based methods, if the dimension is too high, say thousands of dimension, it will take a very, very long time to process this data. So usually we set a cap to this number of documents, and 5,000 is the default value. You can also modify that one to include more vocabularies. And for the pre-processed documents, here is an example which looks like this. So as you can see, it has been cleaned, and inevitably, so this generation of this bag of words will generate certain, for example, some sentence which is completely noisy, it will become empty. So that's why when we actually create this bag of word embedding with the pre-processed documents, we not only generate this bag of words, we also obtain the like the ID2 token, and also I think this return the indices to make sure we remove that. It's over here. We return the indices to remove the empty sentences, both from the bag of word and also the embeddings. So when we load the embeddings for document and the images, we use this one to index. The one could be useful. So this block 7 is about evaluation, which I will mention later. And block 9 over here are setting some training arguments. For example, the learning rate, bag of word size, computational size, for example, the hidden dimension of the neural network layers, and number of epochs, like how many epochs we would like to train till the convergence of this method, and the name of the device. So you can, if you are not using Mac, you can use this one. So you can either run it on CUDA, or you can run it on CPU. And here is the hyperparameter of number of topics. So here, for example, I'm generating 15 topics, and this could be forward once we when we define the model, the VAE model. And the block 10 over here is how we train this topic modeling methods. It has multiple for loops. Let's focus on these first. So this outer for loop was used to do the hyperparameter tuning. Like you can replace this one with a list of number of topics that you want to, that's this one, like the inner loop. The outer one is that we want to test the stability or robustness of the method. So we conducted multiple runs and calculate the average performance this will be particularly useful for some small data sets, which we need to run it multiple times to decide. And here is again our topic model data preparation. So the purpose of this model is to convert our embedding, including the document embedding, image embedding, bag of words, and the relevant tokens to this data loader. So we've covered data loader in previous tutorials. So I'm going to skip it. The only thing I want to emphasize is that how it differs from other data loaders. So it's in the data, these data sets, and within this dataset folder. So the first one, the CTM dataset over here is just for unimodal with only the text embedding. So that's the code used for the CTM model as I shown in the GitHub repository. And we are going to use this one, CTM dataset multimodal. So the only difference is that while we define the dataset, we include all this kind of information, including the image, and we define the image. And one And when we obtain the data for each batch iteratively, we not only give it back the image and the text, we also give them this image embedding. So in this example, it is returned as a dictionary with the name of these kind of different modalities. So bag of words, this is the text embedding and also the image embedding. So that's for the data loader part. And next, we are going to define this CTM method. We are going to train it with this feed function, and we are going to obtain the topic list. So I'm going to first introduce this combined TM, which is a class name of our model. So the model is defined here underneath this models folder, within this models folder. So it is this CTM file. And it has a class of CTM, which is a base class for all of this method. It has functions like the calculation of loss of VAE method. It has this train epoch, which is a training iteration of the method. It also has this feed method, which we will use to start the training of this CTM method. And it also have other functions like validation, get theta, which means get the document topic distribution, which you can try later on, and get document topic distributions, like get the document distributions, includes multiple sampling, reduce the variance. And other functions, we will cover some of them within this tutorial. So at the end of this CTM file, so it has this combined CTM, which inherited this CTM and also zero-shot CTM. So that's the one we were using for the top insight. And we are going to use this combined CTM. That's where we defined over here. So we write down our multimodal code inside this function. So when you define this CTM class, you need to define certain hyperparameters. For example, the bag of word size and also contextual size, which is a hidden dimension, and inference type, which is multimodal. For us, we are using number of components, which means number of topics, and some other important are the hidden size for the encoder decoder, and activation functions, and other things. So I will skip this kind of like detailed information, and you can check later on. Essentially, it defines a model over here. So CTM is a framework with encoder, decoder, and optimization. This CTM class defines the whole framework of VAE-based multimodal classification. In terms of the model, it defines within this decoder, and you will see why it defined in this decoder later in the training process. Right now, I'm going to introduce this decoder network and also encoder network. So all the networks are defined over here, including decoder network, inference network CAT, that's the ablation inference network we used in the paper. And that is our inference network, which is the encoder. So for CTM, it defines the decoder network directly over here. So essentially, the inference type over here. So you can choose either zero-shot, combined, or the multimodal, which is the one we are going to use. And interestingly, within this decoder network, it defines this, within the decoding network, it defines the inference network, which will be the multimodal encoder we are going to use. So let's check this multimodal inference network first, and then the decoder. So this project has some hierarchical. Hopefully it's not that confusing. So for this inference network, so our multimodal inference network is over here. So basically it is the encoder, part of the method we define. I think I will skip the definition over here, and I can always refer back in the forward path to help you understand how the dimension changed. So the first thing we are going to do with the image data is that we need to like reshape its format. It has 512 features for each image. And for each feature, it's represented into these 45 dimensions, which is the output of the massive pooling layer for each kernel. So the first thing we are going to do is to reduce the dimension of these 49. So what we are going to do is we define this adaptive image network. So this one. As you can see, it uses a fully connected layer to convert it from 49 to 1. And you can always refer back to the network structure in terms of how it used. So, and as a result, for this X image, it has a dimension of 512. The reason we put them to the same dimension is for easier calculation, and also it will align with the dimensionality of other bag of words and also the bird. So here is how we conducted with the gate vector. So we have this GMU gate, which is another fully connected layer. It takes the glove as the input. So here the name is a little bit confusing. I apologize for that. So it's not the glove, it's actually the embedding of the text. And so the purpose, if you remember here, is to decide which part of the image is informative or not. We do that by reduce its dimension to the same one as image and use the sigmoid to scale it between 0 and 1. And for the image, we also need to learn this image vector, which is comprised version of the original image. And for the context vector, which combines the image and text embedding, we add the BERT embedding together with this kind of image embedding, which is conditioned on this gating factor, which is a gating vector generated by this BERT. So for the context vector, after that, we combine this context vector with the original bag of word, which is this X, the first arguments of this forward function. For the concatenated results, we conducted several layers of fully connected layers with activation function and also dropout layers. And then with this input X, we learn a mu and also a sigma with this kind of batch normalization just to rescale the dimensionality of this mu and the sigma. And for this inference network, the callback will be the mu, sigma, and the original X. So that's all for the inference network. It will be used in this decoding network. And let's have a look how it looks like. So again, for this structure, for this network, we go to the forward pass. So the value is firstly forward to this inference network, and the output are the learned mu, the sigma, and also hidden dimension. So to calculate the posterior sigma, we need to. It is a common practice in the application to use this expectation to scale its range, and then we generate samples from this theta through the reparameterization trick. So this is conducted by this reparameterization function just over here. Just as we discussed in the previous pass, we sample randomly from a normal distribution with a mean of 0 and a variance of 1. And then we use the reparameterization trick to add the mu to the standard derivation and also include this randomness. So all these 0.5 and other things are derived from this kind of using normal distribution as the prior knowledge. And how do we do that? So things like that. So once we sample this theta, it will be forwarded to the decoder part to conduct the topic modeling. So here, no matter which part of the model type you choose, so the difference are their assumptions toward this prior. For VAE, it tend to use this prod LDA, which assumes the normal distribution of these topic word distribution. So whichever method you are going to use, So the idea is that once we got this sample, we multiply it with beta. So beta here is explicitly defined as as a tensor with the same number of topics and also the same sets as the latent space. So that's the beta. As you can see over here, it is defined as a parameter. So parameter means this beta is learnable and updated with the loss function. So that's how we obtain the beta. One reason we define this beta explicitly is because we want to obtain the topic word distribution. So we want this one. And again, because it is a distribution, so we use this softmax function to generate the distribution of each dimension of beta. So for each dimension for each topic within this beta, its probability can across all the vocabularies can sum to 1. So the return value of the decoder network are the priors, posteriors, which are generated by the encoding network, and the word list. And also, so we are not going to use this one. So for CTM, they have a supervisory version, but you can ignore this. So that's for the decoding network. Let's go back to this VE framework, which is this CTM. So once we define this decoder network, and within it, we all know we define this inference network. So to fit the model, we are going to firstly, we are going to do some batch optimization. So we are going to learn multiple epochs first, and then conducted batch optimization toward this, within this training epoch, we are going to do the batch optimization. So that will be the one. So over here, so that's the one we need to focus. So for this one, it basically calculates the loss given each batch, and the input of the loss are given from this decoder network. And then we calculate the KL divergence and also reconstruction loss. We combine these two together through this function. There will be a hyperparameter called beta to control the value of the KL divergence, like how strict you would like to control the latent space to restrict the learning. So things like that. And we sum up all the losses over this batch. And then we conducted this backward propagation, and we use the optimizer to update the parameters. So and then we can finish the training for each batch. So in terms of these loss, so for this loss calculation, it's also written in a separate function. So basically, those are just some standard method to calculate the KL divergence given the prior and the posterior, which means the prior distribution you define, and also the one learned from the neural encoder part to calculate this KL divergence, assuming the standard normal distribution. So those are standard ways to do that. For the reconstruction loss, so here we use the cross entropy loss to reconstruct the bag of words from the input. So that's the loss function. Basically, after the training of this CTM method, we can obtain the topic lists and then evaluate the quality of each topic. So, and when we do the evaluation, we can choose top up to, like, for example, how many top words you would like to include in the evaluation process. For example, here I tried top 3 words for each topic and also top 10 words, and you will see slightly difference between these two results. So, and in that case, we will, for example, over here, it looks like the top 10 words can have a slightly words performance comparing with 3 words. So things like that. And for the evaluation over here, it depends on this generated topic distribution, topic word distribution, whether you are going to evaluate top 3 or top 10. For example, it's like this. It has 2-dimensional list. The first dimension are word distribution for each topic. The second dimension are all the topics within this list. So we are going to calculate this coherence through this coherence model. So remember, for coherence model, it calculates for each topic how similar context it represented for each word. And we are also going to calculate this NPMI, which is a pairwise evaluation given paired results from the topic list. So we are going to rely on these packages due to, I think, the time. I'm going to skip this part, but feel free to check it. And another thing I think is, I'm not sure if it's over here or within the package. Oh, it's over here. For the diversity, we are using this evaluation package, and we are going to use this inverted RBO method for the evaluation. So it's available over here to calculate the different kinds of like diversities. So there are many options, and this inverted version is one of it. You can also choose, for example, the pure RBO or other things. And if you run this block, what you will obtain are things like that. So first, it will plot you like we are going to use the multimodal CTM, and also the inference network is multimodal. So that's what we write down in the code. And you will also obtain this processing bar, how here I train for 10 epochs and what are the losses and the time. So loss here is relatively large because I think here I only set a very large proportion of the KL divergence. And also we are doing it in an unsupervised method. So so the loss will be slightly large. If you train multiple epochs, it could be reduced. And here the sampling means that we sample from the latent space. So if you go back to this decoder network, so for this beta, we sampled multiple times and use the averaged value. Sorry, I cannot find it right now, but basically it means we sampled multiple times from this decoder network and use the averaged value to as the topic word distribution. And here it print out some evaluation criteria. For example, the RBO diversity, direct diversity without the inverted version of this ranking, and also the coherence and also the NPMI. So they are over here. So this is the coherence, and the NPMI is negative, which means this might be not good. And also we have the diversity and also the inverted rank diversity calculation. So this is the one we reported in the paper. So here I plot the topic list. So this is an example of topic list obtained from the trained CTM model with, I think, with 15 topics. And we are going to evaluate on the top 10 words. So that's why if you check this list, it contains 10 words for each topic. And there will be 15 topics for each of them. So this is just to show you how the topic is it looks like, and we are going to conduct the coherence on each topic and diversity across different kind of topics. So that's how we obtain these theta through this kind of function. So you need to input the vocabulary, your data set, and then you can get this theta. So theta represents the topic distribution. So it has 15 topics, and there are 5,000 of the vocabularies, which is a cap we set. So each topic contains all these kind of word distribution. And when we do the evaluation, we only use the top 3 or top 10, like the most frequent one, to represent each topic. So here is an example of generate the word cloud, which is another way to evaluate the quality of these of each topic. So here I plot the topic 1 with different kind of word, and for this word cloud, you will get a larger size of the word if their proportion is higher, which means their distribution is higher. For example, here the largest one is the, and it corresponds with the most frequent word for this topic as we generated over here, and the next will be there. So this one is ranked according to their contribution to this topic. So you can use this code to generate different topics, and I think that's basically what I want to show you for this tutorial. So let's go back to the slides. So we've covered this network optimization, evaluation, and and now we have several activities for the following. I think you have like half an hour, about 40 minutes. So what you can do is try different number of topics. So in the tutorial, I use 15 topics, but you can try, for example, 5, 10, 20, 50, and then change the epoch to see how it performs. And you can see, for example, if you have 50 topics, could the topics have some overlapping between each topics? You can visualize this through the word cloud, but be careful, it can generate all the topic words for the 50 topics. And you can also try to increase K, and send the effect of the quality of the topic assessments and document reconstruction. So the second activity is about evaluating top words, because that's another hyperparameter which might be used in the work. So you can try to extract the top 3, 5, 10, and 20 words for each topic. So that's the loop within each topic. And you can evaluate what will the model perform with a smaller key value, like top 3 words of each topic, and what's going on with a larger key value. For example, you have 50 or 20 topics to be evaluated for each topic. And the last activity are about the document topic assignment. So you can analyze the document to topic distribution, and for each document, print its topic proportion. So you might need to explore it like within the CTM model and found that function. So it's underneath that, I think, CTM class. And you can see what's going on with each document, and what will happen for each, what are the differences between proportions for the document. So that's basically the activities you can for this tutorial. And now you can have time to play with this code. And if you have any questions, you can we can discuss in the chat. So I will stop sharing over here.
Dewey, for so insightful tutorial and going through all the notes. So participants, if you understand correctly, now Dewey has presented the theoretical concepts. She has presented the hands-on concepts. So it is now your opportunity to make those changes in the codes that are given to you and get the results. And meanwhile, she's here if you have got any questions. So please attempt at your end the 3 activities that she has listed and get the opportunity to ask any questions that you have. Or if you have any other questions related to today's tutorial and hands-on, we have got about half an hour where you can utilize, or 20 minutes or so. So Dewey can answer those questions. Thank you.
Thanks, Richie.
And just a reminder, you do have a quiz based on module 3 and 4 at 3 p.m. today. Okay, may I ask, any of you are trying those activities? This is your golden opportunity because Dewey is around for the next few minutes. So this is your opportunity to ask any specific questions to her if you are attempting the activities there.
We got a question about is there any work that includes audio as well? So our focus is more about the image and the text modalities. And I do see some works about like using videos for clustering-based method. For example, in a wild environment, can we use clustering algorithms to identify what certain of creature within this like environment? But I'm not sure about the topic modeling with audio modality, but it will be very interesting to see the applications in the audio domain.
Yeah, and additionally, as part of Dewey's PhD, she has developed a large number of multimodal classification methods. And we have included audio as one modality in there. So we have some data sets where we have got text, audio, and video.
Thanks, Richie. And we got a very good question. Is there any work related to XAI domain? So I think XAI is very popular in recent years. And but for topic modeling and XAI, I haven't seen too much like overlapping between these two domains. Usually in NLP, the researchers are interested in, for example, developing some XAI-based methods to explain, for example, large language models or other kinds of large models to uncover how the large language models make decisions. And in terms of topic modeling, I'm not sure about this one. One reason probably because for topic modeling, we can always obtain these two distributions mentioned in the course. So some people will say VE is better at the explainability than other method because it's graphical based method. And also we can obtain this kind of distributions, which is partially explainable. However, it's not actually completely explainable in terms of this XAI thing. And we also get a question about the generalization ability of the proposed model. So in our work, so I think the generalization ability partially depends on the feature extraction methods. So here we use VGG19 and BERT for the embedding. So even though so we don't use any fine-tuning method to obtain it, because we think the vector obtained in most of the general tasks, like these kind of social media crisis event detection or the other similar tasks, they are representative enough. However, we do notice that under certain domain, it is needed to like fine-tuning these two embeddings to make it more general, in order to adapt to certain specific task. So it quite depends on this contextual embedding part. And another question is, how does mismatch in embedding affect the performance? This is a very good question. So the mismatch about this multimodal embedding is a very common phenomenon of the multimodal learning. So for example, in certain domain, like for example in social media, let's say. So sometimes the text is not that representative, because, for example, if we collect it on social media, people tend to see very vague things about a scenario or something else. However, other modalities could be more representative. So in that case, one thing we have been observed is that, for example, even though you combine multiple modalities, the performance on these downstream tasks will actually not as good even as the best unimodal performance. So in this topic modeling case, for example, in our experiments, without using this gating mechanism, sometimes the performance of the multimodal topic modeling will be lower than the unimodal topic modeling method, which is at CTM baseline. So that's how this mismatch will affect the learning, because we think this is because of the mismatch, it introduced extra noise instead of actual context information to the context, to the embedding, which will actually affect the learning instead of boost the performance. So this is quite essential in these in all of the multimodal tasks. And we got another question about, are we giving more weight to image compared to text? So the weights so the weights of the image is and the text are learnable with this neural network architecture. And in our framework, because of the data set we are using, we assume that the text is more has more direct or more close relationship with the topic generated compared with image. So in our work, we actually restrict the contribution of the image. In other words, we tend to restrict the weight of the image compared to text. And that's all depends on our assumption while building the multimodal framework. And it quite depends on your domain and on your task. For example, in certain tasks, the image could contribute more compared with text. But usually in most of the multimodal learning tasks, this kind of contribution are learnable because there is no general pattern. Most of them do not have this general pattern. For example, one modality contribute more than others, or they always contribute equally because of the mismatch thing mentioned before. So a learnable weight using deep learning method can make sure that for each instance, it dynamically generates this kind of adjustment and fits the task.
So So this is one of our latest work as well, as part of Dewey's research, where we learned the effect of each modality and each instance dynamically, because in the multimodalities, there are many issues where one modality is more important for a certain task, where other modality is not so important. And sometimes within the same modality, one instance may have more useful information than another. So how do you do this kind of weighting and learning automatically? That is Dewey's latest work.
And another question is how multimodal models are different from ensemble model. So this is a very good question. So for when we refer to multimodal, we emphasize on the input modalities. For example, we have image, we have text. And when we talk about ensemble model, it's more about like the framework or the algorithm you are going to use. For example, we use the XGBoost, which builds multiple trees. And this is one of the ensemble model. And it can be applied to unimodal data, for example, with tabular data and XGBoost. And ensemble method also work for the multimodal data. For example, some methods I've seen in the medical domain, given the different kind of image modality like CT image and also MRI, they build ensemble model for image and the text different image modalities respectively, and then use their the decision score of all these methods within this ensemble framework to generate the result. So in general, multimodal refers to emphasize on the input data set, and ensemble model emphasize on this algorithm.
And if I add there, so the process that Dewey was mentioning, a lot of time we call it as late fusion in multimodal. So ensemble model is usually you have different algorithms running a unique part of the learning problem. Whereas the multimodality model, what they do, they try to learn the inference between the data at data level or at intermediate level or at inference level, and then model those learning process and do the learning simultaneously. So they are quite a different thing, but sometimes you can see multimodality late fusion as ensemble model. Otherwise, ensemble model is usually ensembling of different algorithms and their decision-making progress.
Thanks, Richie. And it's good to see the interest regarding the multimodal learning. And here is a good question. So the question is about the overall complexity of the model and can we use it at real time? This is a very good question. So so when I did my internship, I tried different kind of topic modeling methods. Now this multimodal one, but the CTM method on the dataset of that company, and they have millions of data instead of just like few thousands of data. What I have found that it's really hard to apply this kind of CTM-based methods and use it in real time. What they usually do is they run the model overnight, and then they can obtain the results in the morning and maybe report the results to others during the daytime. But for some methods, for example, per topic, and I think NMF, if you set the latent dimension to a relatively small value, for example, 5 or 3, it is possible to run those kind of algorithm in real time and obtain just real time like results. But in general, for the statistical methods like LDA and this VAE-based method, currently, if you want to run it from the scratch, it's really hard to like use it at real time. But if you have enough and the representative method data, and you train it. And then for the test time, you only inference from this model without training it again. Then it is possible to use it at real time.
Thank you, everyone. So it was great to utilize the last few minutes of the presentation in answering your questions. You will also have some opportunity in the last day of this course, 2nd February, to have some one-on-one conversation with the team. So I'll encourage you to reflect on these modules, relate to your research, relate to your working, where you organization, or like how you could use it. And we would have some opportunity to answer your questions or discuss those ideas and then explore further collaboration in future. So I think I'll take this time now to wrap up. So I asked Dewey to just wrap the session, just recap the main points that are covered in this session, and we'll wrap it up, and good luck with your quiz.
Okay, so here is a quick summarization of this tutorial. Here we introduce this JDM-NTM, which is a multimodal topic modeling framework that leverage variational autoencoders to model topics as probabilistic distributions. And it integrates multiple modalities like image and text to uncover richer and shared latent topics. And we also aim to understand how JDM-NTM integrates multimodal data to uncover the complex topics. Specifically, we introduce the gated module to address that mismatch problem. And we learn to evaluate multimodal topic quality using coherence matrix and latent space analysis, which is through that the word cloud. And we also gain some practical skills to apply this JDM-NTM to real-world multimodal datasets. So that's basically all for this tutorial. And I will stop sharing over here. So thanks for joining us during this Saturday afternoon. And I wish you good luck in the quiz.
Thank you so much, Dewey. So thanks for attending this module. Please listen to the recording again. I know it could be overwhelming for some of you who were not really were in the field of topic modeling. But as I said in one of my response to the chat, that due to the time constraint, we could not really cover so much of the basic of topic modeling. But do we try to kind of give you the enough introduction for you to understand the rest of the concepts? But the main purpose of this module was how to use, because topic modeling is established NLP, natural language processing method, or text mining method. The people who work with text data may be quite familiar with topic modeling. It's a quite established field. One of the best known topic modeling methods, kind of LDA, NMF, have been around for years, kind of like 1990s. So people use it quite significantly. But in this module, we wanted to show that how this traditional topic modeling can be done by using some advanced GenAI methods. So I hope you will find it useful. If it was too much for you to be understanding in the one go, I highly encourage you to go through the slides again, go through the recording once it becomes available, and the code you already have got, and then try to understand this field. This is quite an evolving field and of emerging importance. So good luck with your quiz today. Me and Dewey will leave the call now and leave it to you with the academy. And I'll again see you tomorrow with Stephen that actually builds upon what we have been seeing in Bashar's and Dewey's talk, where we use LLMs for the text generation and how can we ensure that the generated text is of high quality. So that's what we are going to look at tomorrow, LLMs as generators. So thank you very much. Thank you so much, Dewey. And I hand it over to Namita now.
Yeah. Thank you, Dewey.
everyone.
Thank you, Richie. Very nice presentation, very nice examples, so insightful, and everyone has got some takeaways. Of course, we understand it's overwhelming for some of them, but of course, we can do it later as well, having the recordings with us and the slides and the code. So, thank you so much. So I have an announcement for the quiz because we have already announced. It is a pre-announced, so we cannot make it early. We have to do it from the 3 p.m. onwards. So in case of need, you can contact us again, first thing. Second announcement for tomorrow's lecture, as I have discussed with Dr. Richie, we are considering the Republic Day celebration tomorrow. I proposed to Richie that can we adjust from 9 a.m. to 10 a.m. and she agreed. Thank you very much. So we'll be starting tomorrow from 10 a.m. Then we'll continue till 12. Then 45 minutes lunch break, and then we'll continue again. That's all. So we'll adjust somehow to celebrate the Patriotic Day tomorrow as Republic Day. So anyhow, we have to have a trade-off with the lectures and the celebrations and everything. So kindly let me know if in case you find some difficulty. So I hope we'll be able to make it. Thank you so much. During the quiz, we are available here at WebEx. In case of need, kindly let us know.